Alright, let's look at the practice exam 2, problem number 8. Alright, so we want to find the orthogonal trajectories of the family of curves, x squared plus 2y squared equals k squares. Alright, so those are ellipses, right? So we want to find the orthogonal trajectories, right? So first thing we want to do is we want to find out the slopes of the original ellipses. Alright, so let's find the derivative. So by taking a derivative with respect to x, right, so this is an implicit differentiation. Right, derivative of x squared would be just 2x. Right, and the derivative of 2y squared would be 2 times 2 is 4, and y, and then you have to multiply by dy over dx. Right, just a chain rule there. Right, and derivative of the right hand side, k squared is a constant, so it's going to be 0. Right, and since we're interested in the slope, so we have to find dy over dx. So I'm going to try to isolate that. So first thing I would do is I'm going to get rid of 2x by subtracting 2x. So we get 4y dy over dx, and this is equal to negative 2x. Right? Then we can divide both sides by 4y so that we can isolate dy over dx, which is going to be equal to negative 2x over 4y. Right, so we can cancel 2 and 4, so you get 2 on the bottom. So you're going to get negative x over 2y. Right, so this represents the slope of the tangent lines to these ellipses. Right, so since orthogonal trajectories are perpendicular to those ellipses whenever they intersect, so the slope of the orthogonal trajectories should be the negative reciprocal of this guy. Right, so orthogonal trajectories must satisfy dy over dx, right, is equal to, right, this has, we have to take the negative reciprocal, right, so negative sign will cancel out and the reciprocal, so put it upside down. So this is the differential equation that the orthogonal trajectories must satisfy. All right, so then after that we just have to solve this differential equation, right? And this is a separable equation, so we're going to put all the y's on the left, everything else on the right, right? So first step would be I'm going to divide through by y, right? So you're going to get the 1 over y times dy over dx is equal to 2 over x. Right, then I'm going to go ahead and integrate with respect to x. So integrate this side with respect to x, integrate the right hand side with respect to x. Right, then we can cancel dx on top and dx on the bottom. Right, then if you find the antiderivative, that would be antiderivative 1 over y would be natural log of absolute value of y, and which is equal to, right, antiderivative 2 over x. So 2 is just a constant, I'll put it here. Then antiderivative 1 over x is natural log of absolute value of x. And then you have a plus some constant c. Right, and one thing we can do is we have 2 here. Instead of putting a 2 here, using log property, we can put it as a square. Right, so we can rewrite it as a natural log of x squared. Since it's already squared, it's never negative, so we don't really need the absolute value sign. Right, but the plus some constant c. right? Actually, I'm going to call it the C1, right? C1. All right, then we need to isolate y. So in order to get rid of this natural log, what we can do is we can raise e to both sides, right? If you raise e to both sides, you're going to get the absolute value of y, because e and natural log cancel out. Right, then you're going to get the right-hand side is going to be e to the natural log of x squared plus c1. Right, but we can split this using exponential property. You have e to the natural log of x squared, and then you have another e to the c1, right? Then you can see that again, e and natural log cancel out. You get x squared there. All right, then we need to get rid of the absolute value sign, right? So in order to get rid of absolute value, we have to consider plus or minus, right? And then you have a constant e to the c1, and then you have x squared, right? Then there's no point of using a very complicated expression for just a constant. So since this is plus or minus e to the c1, it's just a constant, I'm going to call that constant c. Right? So therefore, we have a family of curves, orthogonal trajectories, which is written as y is equal to some constant c times x squared. Right? So these are the equations for the orthogonal trajectories that we're looking for. Right? That's it. I hope that this was clear.